The drill floor shakes at 3 in the morning somewhere in the Permian Basin of West Texas. A steel tower rises 40 meters above the desert floor, lit white against a black sky, and at its heart a column of pipe, each joint 30 feet long, each one weighing roughly 300 pounds, descends into a hole not much wider than a dinner plate. 3 kilometers below the surface, hidden from every instrument a person can physically touch, something is happening that most engineers working above ground never fully picture. That column of pipe is turning a corner. Not a gentle curve measured in miles, but a deliberate, engineered bend that brings the drill from pointing straight down to pointing perfectly sideways, aimed at a thin seam of oil-soaked rock that the surface rig is not even sitting above. The bit is drilling sideways, miles away from where it started, in the dark, under pressure that would kill a person in a fraction of a second, guided by instruments reading through miles of solid earth. The question worth stopping on is this: how do you steer something you cannot see, cannot reach, and cannot touch, through rock that has never been disturbed in 400 million years, to hit a target the size of a 2-lane road buried kilometers underground? The common-sense answer most people reach for is that you simply tilt the drill pipe at the surface and let the angle carry the bit where you want it. That answer is wrong in almost every respect, and understanding why it is wrong is exactly what unlocks the real engineering. By the end of this, you will be able to explain the actual trick to someone else in 2 sentences, and it will seem stranger to them than anything they expected. To understand directional drilling, you have to start with a fact about the rock itself. The formations that hold oil and natural gas are almost never thick, vertical columns of porous stone sitting conveniently beneath a single point on the surface. They are thin, flat, horizontal layers, sometimes only a few meters thick, stretched out laterally for miles like pages in a book pressed flat under the weight of everything above them. A vertical well punches through that page at 90 degrees, which means it contacts maybe 3 or 4 meters of productive rock. A horizontal well, one that travels sideways through that same layer for a kilometer or more, contacts 1,000 meters of the same reservoir. The geometry multiplies recovery from a single well by a factor that can reach 10 or 20 times. That is not a marginal improvement. That is the difference between an uneconomical hole and a well that produces for decades. But producing the horizontal well requires solving what is essentially a navigation problem at depths and pressures that make every obvious solution useless. You cannot run a wire down the pipe to physically pull the bit sideways. You cannot see through rock. You cannot stop every few hours, pull 3 kilometers of pipe back to the surface, look at where the bit ended up, and replan your route, or rather, you could, but at a day-trip cost of hundreds of thousands of dollars per interruption, you would never drill a commercial well. The engineers who solved this problem in the 1970s and 1980s reached for a mechanism that is quiet enough to be invisible: the mud motor. Every drill string pumps drilling fluid, called mud, down the inside of the pipe continuously. That fluid cools the bit, carries rock cuttings back to the surface, and maintains wellbore pressure. What the mud motor does is convert the flow of that fluid into rotational power at the very bottom of the drill string, right above the bit, without requiring the entire pipe above it to rotate. The motor is essentially a progressive cavity device, a helical steel rotor inside a rubber-lined helical stator, and the pressurized mud flowing through it spins the rotor. The torque produced is then transmitted directly to the bit. Mud motors used in commercial drilling can generate several hundred foot-pounds of torque and spin the bit at anywhere from roughly 60 to 200 rotations per minute, all powered entirely by fluid pressure from the surface pump. Now here is where the geometry becomes interesting. Attached directly above the mud motor is a short, angled sub, a piece of pipe machined with a slight bend, typically between 1 and 3 degrees. When you hold the entire drill string stationary from the surface and let only the motor turn the bit, that bent sub acts like a deflection wedge. The bit is no longer pointing in exactly the same direction as the pipe above it. It is pointing a fraction of a degree off-center. 1 degree sounds trivial, but over 30 meters of drilling, 1 degree of continuous deflection produces a curve with a radius of roughly 30 meters, roughly as tight as the turning circle of a city bus. That is the build section, the arc from vertical to horizontal, accomplished underground without a single human hand touching the bit. Directional drillers speak of dogleg severity, the rate at which the wellbore changes angle, typically measured in degrees per 30 meters. A moderate well might build angle at 6 degrees per 30 meters, curving gently over 5 or 600 meters before going horizontal. A high build rate well in a shale formation with a shallow reservoir might push past 12 or 15 degrees per 30 meters, bending far more aggressively. The physics that limits this is not the strength of the rock. It is the fatigue life of the steel pipe dragged around that curve thousands of times as the string rotates. Bend steel repeatedly around a tight radius and it eventually fractures. Engineers calculate acceptable dogleg severity precisely to keep the pipe stress below the threshold that causes fatigue failure over the planned lifetime of the well. When you want to drill straight, you rotate the entire string from the surface. Now the bent sub spins with everything else and its deflection averages out to zero. You go straight. When you want to turn, you stop rotating the string, hold it at the correct azimuth using surface controls, and let the mud motor do the work with the bend pointing in the desired direction. This alternation between rotating to go straight and sliding to turn is the fundamental steering cycle, and it has been the backbone of directional drilling for roughly 40 years. Here is the midpoint question worth sitting with for a moment: which part of this system would you least want to be responsible for? The pipe under 3 kilometers of tension, the bit grinding through quartz at 1,000 pounds per square inch of differential pressure, or the navigation itself? Tell the channel below. The navigation is where the engineering becomes genuinely strange. All of that steering is meaningless if you do not know where you are. And this is the belief that most people carry without examining it. They assume the driller looks at some kind of readout on the surface that shows a live map of where the bit is, updated in real time, the way a GPS updates your position on your phone screen. The engineers do exactly the opposite of what that image implies. There is no wire. There is no live electrical signal traveling up the pipe. There is no GPS signal underground. What there is, inside the bottom hole assembly just above the mud motor, is a package of instruments, accelerometers, magnetometers, and gyroscopes, that measure the inclination of the wellbore and its azimuth relative to magnetic north, thousands of feet below the surface. These instruments are the measurement while drilling package, and they have to send their readings to the surface through 3 kilometers of steel pipe and rock using the only channel available, the drilling mud itself. The technique is called mud pulse telemetry. A valve inside the bottom hole assembly opens and closes in precise pulses, restricting the flow of mud and creating pressure waves that travel up the fluid column at roughly the speed of sound in liquid, close to 1200 meters per second. Those pulses encode binary data, and the pressure transducers on the surface read them the way a telegraph operator reads Morse code. A typical mud pulse system transmits data at somewhere between 1 and 12 bits per second. That is not a misprint. 12 bits per second, when a modern Wi-Fi connection moves millions of times that volume. But 12 bits per second, interpreted correctly, is enough to know your inclination to within a fraction of a degree and your azimuth to within 1 degree, enough to guide a bit to a target the width of a 2-lane road, 4 kilometers underground, 3 kilometers horizontally away from where you started. More recently, electromagnetic telemetry systems have pushed transmission rates higher, and rotary steerable systems have replaced the slide and rotate cycle with continuous active steering. Small pads inside the tool push against the wellbore wall to deflect the bit even while the whole string rotates, improving both speed and smoothness of the well path. The most advanced systems feed inclination and azimuth data through these higher bandwidth channels into surface software that models the well path in 3 dimensions and flags when the trajectory is drifting from plan. The trick, reduced to the 2 sentences worth repeating to someone: a slight bend just above the motor, held at the right angle while the mud spins the bit, curves the wellbore underground. The mud itself carries the position data back to the surface in pressure pulses, so the driller always knows where the bend is pointing. 3 kilometers down, in rock that formed before the first fish walked on land, a steel tool the width of a dinner plate is navigating by pressure waves through fluid, bending a hole through solid earth with a precision that rivals a surgeon. Nobody sees it happen. Nobody can. But the oil in the pipeline, and the engineering logic underneath it, are both real, and now you have seen both. The bigger the machine, the simpler the trick that makes it work. Subscribe to see the hidden engineering behind the giants around you.